Problem number 21. A uniform bar of length L and mass m is supported by a fixed pivot, a distance x from its center. The bar is released from rest from a horizontal position. The period of the resulting oscillations is minimal when x equal which one? Solution for problem number 21. This bar is a physical pendulum, and for physical pendulum we have a formula for period. Period equal 2 pi multiplied by square root from I over mgx, where I is a moment of inertia, m is mass, g is acceleration of free fall, and x is distance from the pivot to the center of mass. For uniform bar we have a formula for moment of inertia I. Due to parallel axis theorem, that's equal 1 over 12 ml square plus mx square. Now we can put this expression to this period formula, and we have period equal this expression. To find what is the condition for minimal period, we have to find what is the condition for minimum of this function under the square root. For that we have to do first derivative from this function. This is the function. For the extremum of this function we have first derivative equal 0. It means that we have this equation, and after all x equal L over square root from 12. Also we can find what is this period. Minimum period equal this expression, but the answer for this problem is x equal L over square root from 12, which is answer B. That was solution for problem number 21. Problem number 22. Two particles of mass m are connected by pulleys as shown. The mass on the left is given a small horizontal velocity and oscillates back and forth. The mass on the right will behave like this. Solution for problem number 22. The mass on the right will oscillate because the tension in the string oscillates. However, it cannot oscillate horizontally because there is no torque exerted on it. Suppose it oscillates horizontally with no net motion. Then the average y component of the tension acting on the mass on the left is equal to mg, but the x component of the tension is non-zero. Then the average magnitude of the tension is greater than mg, a contradiction. Thus the right mass must instead oscillate and move upward. This is the answer B. Oscillates vertically and with a net upward motion. That was solution for problem number 22. Problem number 23. Two particles with mass m1 and m2 are connected by a massless rigid rod of length L and placed on a horizontal frictionless table. At time t equals 0, the first mass receives an impulse perpendicular to the rod, giving it speed v. At this moment the second mass is at rest. The next time the second mass is at rest is next one. Solution for problem number 23. The motion is the superposition of two motions, uniform translation of both masses with the speed. V center of mass equal this expression, and the circular motion about the common center of mass, where the first mass has a speed v1 equal this expression. The second mass comes to rest again after one period of circular motion. The radius of motion for the first mass is equal to this expression. So after that we can find what is a period. That will be period equal 2 pi r over v1, which is, after we use these two expressions, 2 pi l over v. That's answer A. And this is the correct solution for problem number 23. Problem number 24. A particle of mass m is placed at the center of a hemispherical shell of radius r and mass density sigma, where sigma has dimensions of kilograms per square meter. The gravitational force of the shell on the particle is next one. Solution for problem number 24. By Newton's third law, it is equivalent to find the force of the particle on the shell. The pressure exerted on the shell is this one. P equal gm sigma over r square. Now consider a closed hemisphere filled with a gas of pressure P. Since the hemisphere cannot move on its own, the net force on the flat face is equal to the net force on the curved face, which is equal to area of this flat face multiplied by pressure, which is pi gm sigma. And this is answer E, and this is the solution for problem number 24. Problem number 25. A student is measuring the surface area of a cylindrical wire. The student measures the radius of the wire to be 1 plus minus 0.1 centimeters, using a ruler, and the length of the wire to be 1.00 plus minus 0.01 meters, using a meter stick. The precision of their results can be increased in several ways. First one. Upgrade the ruler to a caliper with uncertainty 0.01 centimeters. Second one. Upgrade the meter stick to a tape measure with uncertainty 0.001 meters. Third one. Repeat the measurement independently 10 times and average the results. How do the resulting uncertainties of the measurements compare? Solution for problem number 25. In this solution we use fractional uncertainties. Fractional uncertainty of an average of n independent trials is decreased by a factor 1 over square root from n. The surface area is proportional to radius times the length, so we add the fractional uncertainties in the quadrature. Then for the first method we have this formula, which is 1.4%. For the second method we have about 10% uncertainty. For the third method we have uncertainty 3.3%. Then method 2 has the highest uncertainty and method 1 has the lowest. The answer for this problem is D. And that was a solution for problem number 25.